So now let's take a look at another example of association and causality. In fact, a famous example of causality that comes from London in the 1800s. Now, if you're familiar with London, or if you know anything about London in the 1800s, it was a dirty and disease-ridden place. And they were facing at the time the problem of cholera. Cholera is a really bad disease, and it was killing a lot of people. Now, at the time, people didn't have a good idea about how diseases spread. It was honestly a lot like 2020. So people believed, this was maybe the main belief about disease spread, that diseases were spread by bad smells. This was the theory of miasmas or miasmatism, and the people who believed it were called miasmatists. So it kind of makes sense. If you're walking down the street, you see some rotting waste, you smell it, it makes you feel sick to your stomach, and you see a lot of death around waste because, as we know now, there were germs, and the waste was harboring the germs and causing disease. But at the time, you mostly associated it with smells, and so you said smells were actually the cause of disease. So if that's what you believe, you're going to do a bunch of things like fly to clean air. You're going to leave the city, go to where it smells nice, and you won't get sick. Or you'll carry around a pocket full of posies or flowers so that it kind of masks the smell of the disease. You might even fire off barrels of gunpowder. This was a real thing that people did. The sulfur in the air and the combustion would consume some of the bad smells. Now, this wasn't just a fringe belief. There were some very important and intelligent people who were miasmatists. Florence Nightingale is the founder or the founder of modern nursing and a statistician. Florence Nightingale believed it. Edwin Chadwick, the commissioner of the General Board of Health, believed in this theory. So it had a lot of popular support. John Snow, however, was a scientist who did not believe this theory and had a different idea for how cholera was spreading. So John Snow took a data-centric approach and could arguably be called one of the first data scientists, along with, ironically, Florence Nightingale, who was also one of the first data scientists. So what John Snow did is gathered data and plotted it on a map. He did exploratory data analysis. So let's take a look, if we can zoom in here. Let's take a look at the map that John Snow made. So if we zoom in, you can see we have all the streets in a region of London, and we have these bars, and what these bars represent are deaths. So John Snow said, okay, one person died at this address, 4 people died at this address, a lot of people died at this address. And if we zoom out, we see that these deaths seem to cluster around a certain region of the map. And zooming back in, that region is here, Broad Street. And in particular, John Snow noticed that the clustering was around the Broad Street pump. So back then, you would get your water by going out to the street. There would be a pump with a handle, and you would pump water up from underground and then take it back to your house. There was no plumbing. So John Snow started to believe that it was the Broad Street pump that was the source of the issues, and in particular, the water at the Broad Street pump. So he was kind of convinced of this by doing a little bit more research, doing a little bit more analysis. So for instance, he looked around the map and went out here to this house where people died despite living quite far away from Broad Street. In fact, they lived closer to the Warwick Street pump and should have got their water there. Turns out that whenever he did some investigation, the residences of this house, there was an elderly woman who had previously lived on Broad Street, but her family moved her away in order to keep her safe from the disease that was killing so many of her neighbors. Unfortunately, the woman really enjoyed the taste of the Broad Street water and sent someone to go get it every day. There are other tragic stories like this. There are children who would live over here and go to school over here, and they'd walk by the Broad Street pump and get a drink of water on their way to school. Examples like this were tragic, but also convinced John Snow that it was something about the Broad Street pump that was causing the disease. So he was so convinced, he went up to the Broad Street pump and removed its handle and said, "Don't drink this water." and everybody thought he was crazy. Okay, so at the time, no one believed it was the water. The disease at the time was kind of on its downfall. It was on its tail end anyways, so it would take a long time for Jon Snow to get the recognition he deserved. But today, if you go to that spot, if you go to the Broad Street Pump, you'll see that there is a pub named after Jon Snow, so it's the Jon Snow Pub, and you can go in there and get a big glass of tap water. But Jon Snow didn't stop there. He wanted to convince people that it was the water that was causing the disease, that it was something in the water. So we have to know something a little bit about the water supply at the time. There were two major companies that served London. There was Lambeth and there was Southwark and Vauxhall, and each had their own sort of territory. Their territories overlapped, though, in this region here. And that's important. That will play an important role here in a second. So in the context of a study, we've introduced these terms like treatment. A treatment group is the group of people who you're giving the treatment. So back in our chocolate study, the treatment group was the group of people who are receiving the chocolate. On the other hand, you have a control group. That's the group that doesn't receive the chocolate. And what you want to do is see is there a difference between these two groups. So if we treat if we treat London in the 1800s as a study, we have to pick a treatment group and a control group. So the question is, what group should we think of as the treatment group, and what group should we think of as the control group? So I'll let you think about it for a second. You can pause the video here and figure out, is it A, all houses in the region of the overlap should be the treatment, B, houses served by Southwark and Vauxhall, the dirty water, or C, houses served by Lambeth in the region of overlap? So the best answer here is B, houses served by Southwark and Vauxhall, the dirty water company, in the region of the overlap. So a key part of this is that this is the region of overlap. We're specifically looking at the region of overlap. We're not looking at just people served by Southwark and Vauxhall versus people served by Lambeth. Now, the idea is that Southwark and Vauxhall was the dirty water. They were getting their water from a dirty source in the Thames River or some other river. Okay, but you could also argue that, well, maybe the people served by Southwark and Vauxhall were in poorer areas and had less access to medical care. If that's the case, that might be why you see more disease. Or maybe they're living in more industrial areas and it smells worse there. That would kind of reinforce the idea of the miasmatus. So you have to have some way of saying that, no, it's the water that's causing it. And so Jon Snow did something ingenious. He said, there is no difference whatever in the houses or the people receiving the supply of the two water companies or in any of the physical conditions with which they are surrounded in this part of the map. He recognized that you really couldn't argue that, well, the people being served by Southwark and Vauxhall here were dying because of smells, because they're living in the same place as the Lambeth people. They're served by the same company. So if your neighbor has Lambeth and you have Southwark and Vauxhall and you die, well, it's probably because of the water, because everything else is the same between the two of you. So that's the key point here, is that the two groups are similar except for the treatment. Everything else is the same except for the treatment. So here's the data that Snow collected. So looking at the area served by both water companies, in particular, you had 40,000 served by S&V, that was the dirty water. Then you had 26,000 served by Lambeth. The ones, though, that were served by S&V, you had 1,200 cholera deaths, which was 315 deaths per 10,000 houses. But for Lambeth, you only had 37 deaths per 10,000 houses. So you see this big difference. And there's nothing else that you can ascribe that difference to than the water or the source of the water. So does dirty water cause cholera? Yeah, I think so. Okay. Now, you could be a little bit more careful, and in fact, you should be careful as a data scientist. You could say, well, that maybe it was that S&V used lead in their pipes, while Lambeth didn't. and it's lead that causes cholera. And to be honest, we couldn't really refute that. But it comes down to using all of the evidence you have. You have this, which tells you that it's something about S and V, and you also have the testimony of the people who brought water from the pump. And altogether, knowing kind of what you know about disease and biology, you conclude that it's probably the water that's causing the issue. So the key here, the very important thing from John Snow's study, was that the treatment and control groups are similar apart from the treatment. Now, if that's the case, you can take an association and turn it into a causality. Remember before we were taking a look at ice cream cones and shark bites. There was association, but probably not causality. Okay? And that's because there were systematic similarities between the two groups and systematic differences. In this case, we've removed all of those differences. The only difference is the treatment itself. And so since there's no other difference, we have to conclude that the treatment is what caused the difference. So we oftentimes want to establish causality, right? We want to show that something causes this effect. So how do we do that? How do we ensure that the treatment and control groups have no systematic differences other than the treatment? Okay? Because this can be a real problem. So for instance, suppose you're studying the effect of coffee on heart health. In fact, this is a study that's repeated like once every year. Everybody's heard coffee is good for your health or coffee is bad for your health. Well, here's something that has actually happened in studies. People will go and they will gather a bunch of data about people and their habits. They will say, oh, do you drink coffee? And then they will later follow up and look at their heart health. They'll then recognize that the people who drink coffee tend to have poorer heart health. Now, this kind of conflicts other studies which say that coffee kind of helps your health, so they're kind of confused. But what's actually going on here is that when these studies were done, drinking coffee was very highly correlated with smoking, and smoking hurts your heart. So what they were really detecting was not coffee influencing your health. They were seeing that smoking influences your health, and coffee tells you whether or not you're likely to be a smoker. These relationships between the variables, that sort of correlation, that's called a confounding factor. The smoking, in this case, is the confounding factor. These sort of factors are very, very common and very treacherous in what are called observational studies. So an observational study is where you go back and you get data from the past without carefully assigning people to groups in order to mitigate the effect of systematic differences. So how do you get rid of confounding factors? How do you fix this problem? And the answer is, it's very simple, and it's the golden rule, it's the golden standard in science, is the randomized controlled experiment. The idea is you randomly assign individuals to treatment and control groups. Okay? If you do that at random, then the two groups are likely to be similar apart from the treatment. So what you say is, okay, I want to study the effect of coffee on heart health. What I do is I randomly divide people into two groups, and I give one of the groups coffee. There's not going to be a systematic difference now. There can't be the case that the people drinking coffee also are smokers, because I randomly divided the smokers between the two groups, and they'll account for each other. They'll kind of wash each other out. So again, this is called a randomized controlled experiment, or an RCT. And the key thing here is that if I run an RCT and I see an association, I can establish causality. There is causality there. So in a normal quarter, I could ask this question and see sort of the distribution of answers, but now we can just kind of go over the answer here and talk about which of them are likely, but which of these questions cannot be answered by running an RCT. Okay, so I'll let you take a look here for a second. You can pause the video if you want. But let's see. Okay, does daily meditation reduce anxiety? I could do a randomized controlled experiment for this. What I do is I divide people randomly into two groups, and I say, you meditate, you don't measure anxiety after a week or a month. Does playing video games increase aggressive behavior? We could study that similar way. Does smoking cigarettes cause weight loss? Now this is interesting because you get to determine who the mad scientists are in the class based on their answer to this question. Could you randomly divide people into two groups and tell one group to smoke cigarettes and the other group not to, and then to see their weight loss? Yes, technically you could, but ethically you probably can't do that. You probably can't tell people to smoke. And so C is the right answer here. You can't do that. Technically, yes, you can, but ethically you cannot. And ethics is a huge part of data science. So that's it for today's lecture, but I'll leave you with one last note. You shouldn't see the word random and immediately think haphazard. In the case of running an RCT, randomness is good. In fact, it's what you should be doing in order to be careful.